Hello, everyone. My name is Zach with HP Additive Manufacturing Solutions, and welcome to session one of HP's Beyond the Layers, a polymers 3D printing series. If you're familiar with our last webinar series, HP's Beyond the Forge, where we shared everything you need to know about 3D printing with our MetalJet S100, you can now expect to learn and grow your knowledge of our polymers 3D printing solution, the HP MultiJet Fusion platform. In each short 30-minute session, we'll go over a key aspect you'll need to get started with our 3D printer. To kick the series off, we'll go from the ground up with today's topic, how the Jet Fusion 3D printer works and its benefits, presented by application engineer Catone Medellin. As a reminder, we have the Q&A option at the bottom, so submit your questions and we'll try to answer them at the end or get back to you via email. Now, I'm going to hand it over to Catone to get us started. Go ahead, Catone.
Awesome. Thanks, Zach. Thanks for the intro. Yeah, welcome everybody. Excited to kick off the a polymers 3D printing series. So thanks for having the time today to join us. Yeah, looking to divulge 30 minutes of information to everybody. And yeah, if you have any questions, feel free to type them in the chat, and we'll try to get them at the Q&A at the end, or we'll follow up on the email. But yeah, like without further ado, like welcome to HP's Beyond the Layers. Um, Here's the title screen right here, and then yeah, excited to kick this off with y'all. So I just wrote a quick agenda. So for today's session, we're going to start with the cross-segment use cases just to get like some familiarity of who's utilizing the MultiJet Fusion technology, what kind of industries is really like benefiting from this 3D printing solution, and just to give an idea like what's out there and what people are getting done, and maybe get the gears rolling for everyone in today's session. And then we're going to segue into how the MultiJet Fusion process works. So a little deep dive into the printer, what's going on with all these nuts and bolts, and how the whole process looks like, and understanding the thermodynamics of how the parts are actually being printed and generated. And then we're going to move into the workflow as a whole. So not just the printer, but the build unit, the processing station, file preparation, what it looks like to unpack the parts, just to give an idea. We will be diving deeper into that in the future episodes. So this will just be kind of like a general overview, just to give an idea if you are unfamiliar with all the steps. And then finally, we'll do some Q&A again if we have time. But yeah, just that's kind of the layout. So let's start with section one, some use cases. So over the years at HP, I've kind of seen a lot of industries, and it's definitely like very interesting. It's always fresh, and there's always something new going on. So MultiJet Fusion's kind of been applicable to a wide variety of industries, namely like healthcare, orthotics and prosthetics, automotive, consumer goods, industrial, drones recently. But I kind of just want to focus on three major use cases and why MultiJet Fusion was kind of a good fit for these companies, and how they've been able to scale in the future and everything. So the first one, starting off, is with healthcare. So this one is Hanger Clinic. This one's one that I'm pretty familiar with. I worked a lot with, and it's been very interesting to watch their journey as they've definitely like scaled up their production. They started off with one printer, and now they got like a multi-machine fleet, and they're kind of adventuring into different products even. So they started with the ankle foot orthoses. So you can see right here, this is kind of an example build. And they saw an opportunity where, Hanger Clinic, they have like 900 clinics across the US. But yeah, so they've been manufacturing ankle foot orthoses for, years upon years. And they kind of had the idea one day, there's like, okay, 3D is probably the future, because of the custom nature of it, that it can fit with the patients. It can give like a better comfort feel for the patients and everything, and better treatment with that. But they needed a solution where, they could supply 900 clinics across the nation, and also one that like could, they could scale with, and that can meet that like kind of demand. So we got into contact with them, and MultiJet Fusion definitely made sense. It's more of like a production geared manufacturing or additive manufacturing. So and we'll be getting into that in the next section. But so they started off with the polypropylene ankle foot orthoses, and they're able to print, like, this is a full bucket right here. They can print multiple devices, so serving multiple patients. And then they come out of the printer kind of gray like this, but then after some post-processing, some vapor smoothing, you get like a really nice end-use part. So this ankle cuffling right here is fully customized based on patient scans, and then same thing with this foot plate. So it definitely enhanced the treatment for the patient. It allowed for like more unique designs, more cost efficient designs. You're saving a lot of material. And then, because of the nature of MultiJet Fusion, like they're able to, supply that 900 clinic demand. And this is the first device they started with, and they've actually recently moved into cranial orthoses also with 3D printing. So this is their cranial orthoses remodeling helmet that they launched. It's called Sprout 3D. They launched SureStep launched it, part of the Hanger Incorporated. And you can see right here that it's based on the infant's helmet like scan data, and then with the nature of 3D printing, they're able to perforate this design. It's greater comfort for the infant, more breathability. You get cost savings, less material usage, and it's a great fit. So really excited to see that they're using that and they're expanding their portfolio. And that's just like the healthcare example. And then moving into automotive, this is one that's been recently developing. It's called Blazing Rods. This is a custom car automotive shop in California. And so being like a custom car automotive shop, like they really had the need for, custom parts, and they really want to iterate really fast. But then so that kind of lends itself towards 3D printing. But then they also have the demand for like high performing, like high mechanical properties parts that can actually be utilized as end use parts. So unbeknownst to us, they're like using three MJF for quite some time, and they actually featured a lot of multi-jet fusion parts on this car right here they call it the Doughboy, but it's a Chevelle, and they actually won best car at SEMA last year, so like a huge automotive like a show that shows off a bunch of crazy builds. But they won best car, and that's where we noticed that they're using MultiJet Fusion. And so they're already outsourcing the parts. And so we got in contact with them. This is a great like demo piece. And they've been really pleased with how they've been using MultiJet Fusion. You can see the quote right here that they're committed to finding smart and innovative applications of it with every signature part. So, and I've actually visited their facility in person, and they told me that they're still like surprised and like really pleasantly surprised when they print two parts that go into assembly, and like it fits first try. So the dimensional accuracy is definitely like there for them also. And then this final this final segment is I wanted to focus on the eye above drone. So this is in the drone segment. As you know, like poaching is an issue in Africa, and it's kind of like difficult to monitor like miles upon miles of like wild preserves. So this company here, the Eye Above project, started using multi-jet fusion to print their drones because they wanted to, iterate. They wanted to be easily repairable drones, but they also needed like a durable and like a resilient material that can like withstand the weathering and the dust and all the associated like difficulties it is with flying in South Africa and Africa as a whole. So they went with multi-jet fusion for PA-12's durability, as you can see right here, extremely tough and durable. And yeah, whenever there's like an issue, they can easily repair it. They can iterate their parts, and it's lightweight and pretty effective, and they can like deploy it in the field. So I thought this was like a really fascinating project because it's really cool to see like a giant drone like this be like assembled together, multi-jet fusion, but then it's also like a great like mission statement that they're trying to like down like they're trying to negate like poaching and save these animals right here. Okay, so that's just like three segments, and they all kind of chose multi-jet fusion for various reasons, but I kind of want to dive into how it actually works and how I was able to meet like a bunch of different of those reasons, like the throughput or the cost effectiveness or the dimensional accuracy, the mechanical properties. So this second segment right here, I'd like to dive into like how the printer actually works and everything. So this is kind of a cross-sectional view. If you can imagine, you're looking at the front of the build volume, so the XZ plane. You can see right here the build platform. So it is a powder-based technology, and it is like a thermal process. So everything that's going on here is at an elevated temperature. It's hard to kind of see, but as you can imagine, there's a bunch of overhead lamps here that's bringing the entire environment up to a certain processing temperature for this powder. Um, and the reason for that is that we're going to be elevating the powder to a temperature, and then we're going to be applying energy selectively so that it's already like close to the melting point, and then you get that melting where you want it to actually fuse the parts. And then you can get like the coalescence and fusing. But how do we do that? Um, we use what we call fusing agents and detailing agents. And I'll show in this video right here. But this recoder will be heading over in the y-axis, and that'll be spreading a fresh new layer of polymer powder. And then in the x-axis here, the carriage will be coming along, and within this carriage, it houses three print heads and two fusing lamps. And so the print heads are going to be responsible for depositing the fusing agent and the detailing agent. And the fusing agent kind of acts as like a catalyst. So that the fusing agent works in conjunction with the fusing lamps. It lays the print heads laid down where you want your part to fuse, and then that fusing agent, once the fusing lamps passes over it, it absorbs infrared energy, and then that acts as a catalyst to start the polymer powder to melt where the fusing agent is deposited. And then in conjunction with that, the detailing agent is going to be laid on the perimeter of the parts so that you don't get any extra fusing. It sort of acts as a cooling agent. So you get like nice crisp defined edges, dimensional accuracy, and you can see in this demo right here. So the recoder just went. Here's the carriage with the three printheads and the two fusing lamps. And, and you can see here depositing the fusing agent, and then the fusing lamps at the same time are going to be fusing that polymer powder together. And what's interesting also about the throughput is that instead of instead of tracing out the cross-sectional area of the parts you want to get printed, it's sort of like a page-wide print. So no matter if you're like printing one part or like in a whole array of parts in that XY plane, like it takes the same amount of time. So it's page wide. And so really the only thing that's dictating how long your build takes is the Z height. So if you can, really pack your build volume, you can get a lot of parts if you're effective with it. And in the XY density again is like it's all the same. It's really just the Z height that's driving it. So so moving on here, you can see that this is where the part forms. And then like any other additive technology, you go layer by layer. So then you lay down more fusing agent, and then you get more sintered plastic. And then another thing that's sort of different about MultiJet Fusion is that this previous layer here is still molten like plastic. And then when you're laying that new layer on top of them, those two layers are going to interact with each other. And you're going to get, this is kind of like if you can imagine the polymer chains here, they're going to still be molten and they will get entangled. And there's going to be a lot of layer to layer interaction. So what that causes is that you get a lot of, you get the same mechanical properties in the z-axis as you do for xy. And so your final parts are really, you can expect isotropic final parts. So it kind of like eliminates the worry of like having to figure out how to orient your parts because you can rest assured that you're going to get pretty isotropic parts when you're finished. So here's like another breakdown. Um, Here's the overhead lamps. It's bringing, like I said, this is bringing it to an elevated processing temperature. And when you have an elevated processing temperature and you have like all this thermally controlled process, you got to make sure that the plastic has a very like discrete like melting temperature, and that you're not like experiencing continuous melting. And then you also need the plastic to coalesce like very quickly also. So this is kind of just explaining that. Well, this is explaining the fusing agent. So you can see here printing some tensile bars. The fusing agent is deposited there. The the detailing agent is invisible, but you can imagine it's all along the perimeters of this XY cutout. And this is explaining the selectivity. So as this fusing agent is deposited, the fusing lamps come up across it, and you get elevated part temperature that's higher than the melting temperature of the plastic. So you get fusing there, and then the white powder temperature remains lower than the melt temperature. So no excess melting. You get nice defined edges, and then you can see the heat signature here. But here's explaining that yeah, you need to consolidate quickly. Um, so. So really our bread and butter is like semi-crystalline materials. Just so you get like those high mechanical properties. Not if you like do really crystalline materials, then they're going to be brittle. And so you want some sort of malleability. Um, and then here's kind of example of PA12 melting. You can see, it heats up and then it melts at at a very discrete temperature. And then compare that to TPU here, where it's more amorphous and it's gradually melting the entire time. So something like this maybe isn't as good as a semi-crystalline material, but with that being said, we still have TPU in our material portfolio, just some variations. And then this is like the all the rigid materials that we offer. So a lot of polyamides. We do print in polypropylene as well. And then we have a few TPUs. And then we're going to be doing a deep dive into the material properties in the later episode, just like really explaining how each one of these are different, what they bring to the table. So if you're interested with that, for that, make sure you stay tuned also. And then the section three, I want to explain kind of like the 3D workflow. So now we kind of understand what's going on in the printer. That's great, but what does like the whole process look like when you're sending a build? So like any other additive technology, it's going to start with file preparation. You're going to need STLs or 3MF files, you name it. So you put together your build. There's free software that HP offers, or you can use any of the other build managers. Um, but then here, sorry, but then here is the pre-process. So there's like three main pieces of equipment. The processing station here is going to like bookend the process. You're going to sort of start here, then finish the entire process here also. Then there's the printer, of course, and then this piece right here is the build unit. So we went with HP, went with the modular design, which I think is great, because as the printer is as you insert the build unit into the printer, you're going to be printing your build. But then these parts do have to cool because it's a thermal process. But because you can remove the build unit, you can literally just wheel it to another part of your facility, let it sit there and cool down. And while that's cooling, you can insert another build unit into the printer. You do have to do like 15 minutes of in between print like maintenance for the printer, but you can like essentially run the printer like lights out, like back to back builds. And so that's just like another key like bonus for maximizing your throughput, getting all those parts out. But moving back to the processing station, um, when you have like a final build, when you have a build that's finished, you can imagine it's going to be like a 3D volume of powder. So you have to, extract your parts, but then you have a bunch of unused powder. So you reclaim that powder, and then this processing station is going to be where you're going to manage all that reclaimed powder and your new powder. So this will be, connected to two sources, your reclaimed powder and your fresh powder. And then this piece of equipment right here is going to be automatically, mixing the powder. It's going to be running it through sieves and filters. Make sure there's like no contaminants when you're eventually going to reload that back into a build unit for a future print. So for all the materials, you can recycle powder. The refresh ratios is going to be dependent on the material. But for PA12, probably the most popular material, it's going to be around 80% reclaim to 20% new powder incorporated. And so you can use that for subsequent builds later on in your production. And so once you have your build unit loaded up with powder, then you're ready to go, send it to the printer, press start. And then depending on the height of the build, again, it doesn't matter on the XY density or the density of the whole build at all. It's just depending on the height. Um, that's going to dictate how long your build unit will be inside the printer printing. But then once that process is completed, you can extract the build unit, set it aside to cool. Um, and then once that's cool, then you bring it back to the processing station. So there's the bookend of the process. And then you're going to extract your parts and reclaim that unused powder again, and the cycle continues. And so that's kind of like the process at like a overview. And then there's, of course, third party. There's like sandblasting kits. When you extract the parts out, they're going to be covered in a thin film of the unused powder, and so it's good to air blast that off and then sandblast that off eventually or at the end of the process. And then there's a bunch of secondary processing like dyeing and vapor smoothing and coating and what have you. But this whole part right here is the HP. This is the parts that we cover. One final little piece of equipment is the natural cooling unit. This is just if you want to free up that build unit, you can take when your parts are, finished printing and cooling off, you can take the contents of the build and place it into they call it natural cooling unit. And so this is basically just like an insulated build unit like box. And then you can, place that on the shelf right there. Then you can let that cool off also. And then you essentially have freed up a build unit as well. So you can, fill it up again and start another print. So that's just at a glance. Again, we'll be doing a deeper dive on that on episode 2. Um, and then here's kind of the process laid out in a video. So this is actually transferring the build unit contents to the natural cooling unit. So I kind of just want to show this off because, if like companies like Hanger or if you have like a high demanding production facility, this is great. Like this is just like showing off the modularity of the system, and how you can just get like, back-to-back builds like set up in your facility. You don't have to worry about, pieces of equipment being tied up, because you can just, again, just wheel them off, let them cool off, run the printer on a subsequent build, or even just put them in a naturally cooling unit to, cool on a shelf. So I'm just gonna skip around here. Oh, I froze it. But yeah, but again, yeah, we'll be going over the process like more in depth on episode dang. Ruh-roh. My okay, here we go. But yeah, okay, so we'll be going over the process more in depth in episode 2. But yeah, that was kind of like how MultiJet Fusion works at a glance. And then I believe we have some time for Q&A. So I think I saw some hands being raised in the chat.
Yeah, appreciate you, Katon. Thanks for
No
sharing that
problem.
information.
No problem.
Yeah, a question that always comes up is how long does it take to print? I know it's a powder-based system with a build chamber, so say we're printing an entire build chamber worth of parts. How long does that normally take, and what's the cooling process for that?
Yeah, okay. Yeah, that's a great question. So for PA12, again, our most popular, it's going to be dependent on the material. But for a full Z height build, it goes up to 15 inches or 380 millimeters. And so for that, for a full height build, it's going to be just under like 12 hours for the printing process. And then again, that build has to cool. It's going to be dependent on the height and the density of the parts, like the thermal mass that has to cool down.
Hmm.
But for the most part, if you're going to be doing the HP and like recommended natural cooling, that's going to be around 30 hours for a full build of PA12. But then you can also do a fast cool in the processing station, and what that is, you load the build unit into the processing station, you connect it to the hose, and
Hmm.
it circulates cool air throughout the build unit. So that's called fast cooling, and that's going to be around 11 hours, 11 and a half hours for a full height build. Um, but again, yeah, like that 30 hours natural cooling time, like that could just be set aside, and you could be running that printer for a subsequent full build. So you can really like layer your production effectively.
Nice. So with natural cooling, then 12 hours to print, 30 for cooling. We're roughly looking at parts in hand at 48 hours. Is that about right?
Yeah, if you're gonna be doing like natural cooling, yeah.
Nice. Okay. And one more time, what was the build volume dimensions again?
Yes, thanks. I didn't touch up on that, but the build volume is going to be in the X direction, going to be 15 inches, 380 millimeters. The Y axis is going to be 284 millimeters or around 11 inches. And then the Z height is 15 inches also, or 380 millimeters. And we can, send this out in writing afterwards if you need like a reference. But yeah, 15 inches, 11 inches by 15 inches.
Nice. Thank you.
Yeah.
Another question that came in, is there a requirement for gas inerting of the build chamber, specifically with some of our other materials like TPU and PA?
There's no requirement for gas inerting. It's not a gas inerting required process. So no nitrogen or anything like that. Yeah, we just ask that you need kind of like control over humidity at your facility, just to make sure that the powder spreads effectively. So if you could do like a relative humidity range from like 30 to 80%, and then temperature controls, but I'm not quite sure, what the recommended thresholds are off the top of my head. But no, it's not a gas inert process.
Okay, perfect. And then earlier in your presentation, you mentioned some like 15 minutes of maintenance between prints. What kind of is that maintenance, if you can just touch on it a bit?
Yeah, so it is a powder-based technology. So, as the recoder is spreading and the carriage is moving in the opposite axis, you are gonna, experience some. It's not. I wouldn't say it's like a messy process, like super messy, but there's going to be powder buildup within the printer that you're going to want to make sure you vacuum. Clean off some surfaces and just make sure that that's not, accumulating print after print. Then there's just some diagnostic checks. But yeah, it just takes about like if you want to run any print like back to back, it's just like 10 to 15 minutes in between prints for the printer maintenance.
Nice, perfect. Going back to natural versus fast cooling, is there a benefit between the two? Is it something with having to do with dimensional stability? Can you just expand on that with the last couple minutes we have?
Yeah, no problem. Yeah, so because or for the most part, the materials are semi-crystalline, if you're going to be doing fast cooling, I guess you would want to be conscious if you have parts, close to the edges of the build volume, because those are going to be experiencing, a greater gradient. They're going to be cooling off faster than, let's say, the center of the build. So it could be, if you have like a part that's really like demanding dimensionally, maybe natural cooling would be better. But that being said, we don't really experience like any warping, like we shouldn't experience any warping higher than like plus or minus 2 millimeters. But again, it would just depend on what your part actually look like. So I'd love to get in contact with you if you have anything in mind specifically.
Perfect. Amazing, Katone. So I appreciate you answering those questions. It looks like we're at the 30 minutes. So if you submitted additional questions, we'll get back to you via email shortly. I want to thank you, Katone, for presenting today and thank everyone for attending the first session of HP's Beyond the Layers. You'll be receiving an email with today's replay and the registration link for session two, which Katone will also be hosting, called Beneath the Surface, the components powering HP's Jet Fusion 3D printing, where he'll go in depth about the printer, the processing station, the build unit, the natural cooling unit that he touched on, and how they all work together. With that being said, I hope everyone has a great rest of your day, and we look forward to seeing you on the next session. Thanks,
Yeah.
everyone.
Thank you, everybody. Yeah, great questions. Yeah, I'll see you on the next one. Thanks.
Thanks. Bye.
Bye.